How's the level? Should I speed up, go slower? Like, is it just right?
Just right.
That's right.
Right.
Okay. I think I can make it through the whole deck of slides at this speed. So. Shall I start again? Okay, so in a sense, when you can do readout, you can also initialize, right? Because you can initialize through readout. Then when you know. So historically, the way this was done was, I think, a bit stupid. People would put a spin, an electron on the quantum dot, and then either it is the one you want to have the ground state, or it is the excited state, and you just wait until relaxation kicks in, and then you know that you have initialized it. Okay, but in modern platforms, this is approaching almost the second level, right? Like 100 milliseconds. That is becoming very impractical if you need to wait every time that long. So there is, by now, I would say we have developed a whole machinery to deal with that more efficiently. So you initialize through measurement, and then either you reinitialize or you do post-selection. You just take the ones, you post-select the ones that you want. Yeah. We have now FPGAs, etc., that allow you to apply very fast feedback to your spin qubit. So this is an example. Let me think. They have here a window here where they keep monitoring the system and charge center signal. Let me think, why did they... Here, nothing, yes, those two curves, sorry. So they wait a certain amount of time to see if there's a blip, and then they know that they have initialized a certain spin. When they don't observe it after a certain amount of time, they apply a pi pulse basically to flip the electron spin. Okay? The point really, like the technical details, it gets quite technical when you read the papers nowadays. It can be a bit of a task to figure out exactly how they initialize or read out. But the point is that the general principle is always the same. It is spin to charge conversion, and do a charge measurement and somehow link that back to the spin state. And yeah, it's quite evolved and advanced. There's no point in going over all the details today, I would say, but at least you know where to put those type of papers and works in the bigger scheme of things. Okay, this is perhaps the most interesting one. Then I come to your question, like how does this work, spin resonance? And in a sense, a spin system is a model system for any two-level system in quantum mechanics. So if you have worked with qubits before, you probably know this. If you haven't, it's pretty straightforward to follow because luckily it's only a two-level system. All right. So we have the Schrödinger equation, of course. We don't need to, this is pretty basic. We have kinetic energy and potential energy. Let's look at the spin qubit Hamiltonian. So we have the Zeeman Hamiltonian here, magnetic field, spin state. We have some spin qubit, it's a superposition state of the two spin states, so we can define this state. The Zeeman field, we have it, it's just a choice of convenience that is typically done in the community. Have the main field axis along Z. It's still gallium arsenide in this case, right? We still have this level diagram, what I showed before. So we can look at the Schrödinger equation now, what it becomes in this formalism. So this is our spin state, and this is now our Zeeman Hamiltonian. Okay? And this we can just solve. It is not very difficult. I can do it, so it can't be too difficult. So the solution is takes this form, right? And if we now look at a spin, for example, a spin that we initialize into this state along the x-axis, it starts processing. Okay? And this is, I think, well known. You probably had this at some point in undergrad course already when you were 19 or so. This is known as lumot precession in the literature. This is what we call the block sphere in qubit land nowadays. So we project one of the qubit states onto the plus or minus z axis, and this is how we think in our community about qubits, as a complex vector living on the surface of this sphere. Now, how about control? For that, we apply a rotating magnetic field in the plane of the block sphere, okay? So in the XY plane. And this is known as electron spin resonance. It's a very old technique, exactly the same, of course, with nuclear spin resonance, except the frequency range is very different, typically because of the nuclear gyromagnetic ratio being much smaller than the electron gyromagnetic ratio. So this was all figured out in the, experimentally and theoretically in the 40s, 50s, and then many experiments have been done on bulk systems for decades, of course. And we're basically reinventing all that knowledge, not reinventing, but applying it now to devices where we can manipulate single spins and single charges. So we have our static Z field, but now we also have those two components there. And the frequency we apply is exactly the energy difference between the two spin states. So we need to match the Zeeman energy. We plug this into the Schrödinger equation. And we have Pauli spin matrices. We get this Hamiltonian for the Zeeman field now. And again, this is pretty straightforward to solve. I think it's not all complicated. We don't need to go through all the details, I would say. But the point is that our final solution takes this shape. Okay? So, as always with transitions of quantum states, the level spacing determines the excitation frequency. So we need to be on reference with the Zeeman energy that we supply to the system with our static magnetic field. And then how fast you flip the spin, so that is the point, right? The spin now is flipping when you apply this orthogonal oscillating field. And how fast the spin is now flipping depends on the strength of your drive term. So where it is in here. Okay? So yeah, the frequency of how fast you are flipping is directly proportional, linearly proportional to the strength of your drive field. Okay? This is how you can visualize this on the block sphere. So of course we can now do this for a set amount of time, apply not a continuous microwave field with a pulse. And then what starts happening, you have the lumot precession, but on top of it you was making a corkscrew-like trajectory over the block sphere going down. And that is how you perform your flipping end. And then by determining how long you apply the microwave fields, you can actually have accurate control over the superposition state here. Okay? Yeah, and there is of course the whole formalism behind this to do this more conveniently than doing it this algebraic way, solving it. But this is the general idea. I think that should answer your question. So you need to have an oscillating, in this case it is the Zeeman term, but the term that defines your qubit, along one axis you need to have an oscillating component of that same mechanism along the orthogonal, in the orthogonal direction. Yeah, that is the thing. You need to apply a magnetic field, oscillating magnetic field to the spin qubit. Yeah, and you haven't seen that yet in the devices, but okay, we can plot the expectation value. I will show you in a second. We can plot the expectation value of the qubit, the energy expectation value, or in this case we plot the state probability and you get these typical sinusoidal oscillations. And depending how long you apply the pulse, that is the superposition you create. And these are of course known as Rabi oscillations. This is the Rabi model that is behind this. Okay? And this is generic. Now we call it spins and we talk about magnetic fields and G factors, but this is how it works for any qubit, any two-level system, I would say. So there is the next step basically in the development of spin qubits was to, on top of this structure, add a big microwave antenna. So this is the ground planes of a coplanar strip line, and over here you have an oscillating current that generates an oscillating magnetic field. And in general, you need to make sure that this is then orthogonal in direction more or less to the static magnetic field, or at least it has some orthogonal component, and then you can drive the spin. So that is how it got implemented then in real life. All right, I want to, this is sort of, I thought of skipping all this, but we need it tomorrow briefly, so I will introduce this too. Let's now, of course, this is basic. I think we all know this and got this again at some point in undergrad, singlet triplet states of two particles. So we can, from a spin perspective, we can have the singlet state, which is antisymmetric under exchange of the particles. So the whole thing gets a minus sign when you flip the particles, or you can have the triplet state, which is symmetric upon particle exchange. And there we have those three combinations. We have the up-up and the down-down, and we have up-down plus down-up. So the sign is here. The point is that the triplet state of the singlet state has the lower energy, and there's an energy difference between singlet and triplet. Okay? And this is a small energy scale. It's much smaller in these systems. It's determined by how strong you couple two electrons, two neighboring dots, how much the wave functions overlap essentially. But this energy scale is much smaller than the charging energy. But we need it. And the reason we need it is that we can now use a different way readout mechanism, which is called Pauli blockade. And it's called Pauli blockade because it relies on Pauli exclusion principle. So now we have, instead of a single dot, we have two dots in between source and drain. Both of them have a spin. And the point is that we tune the system in such a way that having a singlet on this extra ancilla dot here is possible, but a triplet, because of its higher energy, is not accessible. So depending on what spin we have, we can either form a singlet on this dot or a triplet. Okay? And this is the corresponding level diagram. There is an energy difference between the triplet state and the singlet state on this ancilla dot, and we make sure that the triplet sits above our available window here, but the singlet sits below, meaning that the spin down electron can form the singlet and you can have transport through the structure, so you can tunnel out and observe this tunnel event, whereas the spin up cannot form the singlet, it needs to go to this higher energy state, and that is blocked. Okay? So in quantum dot spin qubit language, we call this the singlet 1-1, one electron on each dot forming a singlet, and that you can convert into a singlet 0-2, 0 electrons here, 2 here, but the triplet 1-1 formed by the 1-1 charge state, you cannot convert into a triplet 0-2. Additional mechanism to do also spin to charge conversion, basically. In the one case, there's a charge transfer happening, in the other one, not. Quickly look at this. Yep.
But again, in terms of quantum manipulation with spin, it makes sense if you have some means to make the phase relatively weak. Right? I mean T2.
Yeah.
What to do? I don't understand. Is there any way to make T2 in this system relatively low?
You mean that it is a long time scale?
Yes.
Yeah. This is mostly determined by material properties, and then we can play tricks. I will show some tricks in a second, like we can do dynamical decoupling, like we can use spin resonance techniques to keep the coherence correct, basically, for some of the phasing mechanisms. But ultimately, this is the limitation of your system. And gallium arsenide was not favorable, and it is basically phased out for exactly that reason. Platforms based on silicon and germanium are much more promising, and I would say T2 star, T2 is no longer the real problem there of the single qubit. So just for now, accept that experimentally this is possible. We can do things. I will show some nice results in a second. Okay, so this is just the same story, but now with some energy diagrams, with an energy diagram added to it. So this is in case of well-separated electrons, no coupling to it. We can draw these various lines corresponding to the various states. And on this axis here now is how much you, what we call detune the dot, okay? So the relative difference in potential between the dots. Now, if we turn on this tunnel coupling between the dots, you get an energy splitting here, and yeah, you can see that you can stay in this state, but this one here, you can hop over to form the singlet. This you can hop over to form the singlet to 0, but the triplet 02 is not possible. Alright, so in experiment, how does it then look like? You initialize, you know, this is the ancilla dot, so really this is like an idle dot, an idle spin qubit if you wish, that doesn't do much, we only use it for readout. So you initialize with a spin up or spin down. You will find that when it was spin up, you are blockaded, so you cannot have transport. But then you can do something to it potentially, so you can do an ESR close to flip it, and you can unblock the current through the system, because you can form 02, and this can tunnel out. Okay? So you have this scheme that either you form singlet 1-1, and you can have, you know, within the tunnel times of the system, you can observe a current blip here, or you formed a triplet, and you can perform ESR to flip one of the spins, to flip the spin and unlock the current. And also, of course, there can be a decay mechanism. That is the T2 that we're talking about. If something makes the triplet decay to a singlet, you also can unblock it, but that is an unwanted form because we cannot control it. Okay, so that is the mechanisms that we can now form this singlet 02, which allows for transport. And this is then the actual experiment where people did this again for the first time. So you can see that the time is slowly progressing. We're now in 2006. The graphs are getting more colorful. We started with only lines, and now we have color plots. So on this axis, we have magnetic field. We have here excitation frequency. So this is a continuous driving microwave field. So it's not in a pulse fashion, but in a continuous field. And here, because this was done in gallium arsenide, because of the nuclear spins there, everything is mixed at 0, so the whole thing doesn't work. But once you apply a little bit of magnetic field, so in this case about 50 millitesla or so is enough, you can start seeing this mechanism at work. When we hit the resonance frequency, and this is now the single triplet splitting that we are addressing, then yeah, you see this line. Okay. So this tells you that this readout mechanism based on Pauli exclusion principle, basically, that you cannot occupy this triplet state, it works. This was the first demonstration of it. Here you see a line trace. So this is femtoamperes. You're measuring peaks here of like 200 femtoamperes. So it's pretty weak signals, but it works. This is time average. This is a continuous driving field, and you have continuously some extra current on. Then the Rabi oscillations that you now make, how is that then implemented to tie everything together? How do you do that? You tunnel on with an electron here. Then You tune the system in a regime of Coulomb blockade, so you don't see any current. You try and do your electron spin resonance, and then you pulse the system to this dot to the point where it can tunnel into this singlet 02 state. Okay? So it's a game of first allowing an electron to tunnel in, then we put all the levels below this Fermi level, so we cannot have any tunneling in or out of the system, and that is when we do our operation. And then to check what we actually performed, you pull this level above the singlet 02 level and the triplet 20 stays way out of range here. Okay? And that is how it was implemented in the experiment. And using this is the double dot device here, operated in the way I just described. This cannot be the same device, like this is the real device, but of course for a paper you don't see anything when you put the microwave antenna right on top of it. So underneath here you have this device and the microwave antenna sits right on top of it, and they apply this sequence. So I have the system tuned up, they apply this gate voltage to load an electron, then they put everything in Coulomb blockade, so you cannot have any transport, but now you can operate on this spin. And then when you do this as a function of pulse length, you start seeing these oscillations. And this is coherent control of a single electron spin. Yeah?
In the experiment, we do not touch the right quantum dot, we just initialize it with one speed, and we manipulate it with the left one.
Yeah.
Okay. So, how would this happen? Is it just a plunger, or we touch the barriers?
For this specific experiment, I would have to check the paper, but in reality, you need to adjust all the gates. But usually there's a linear dependence between them, and you can apply a single, once you have characterized the system, because usually a barrier gate will also affect, like this gate over here will also have some effect on this gate, on this electron here, but you can correct for that. So basically you need to, you apply a compensating voltage to this pulse, to this gate, for example. So we can play these tricks, but it's under the hood a little bit, like it's part of the characterization of your quantum dots.
How actually in the experiment determine, do I have a loss of intensity with this one speed, or I have a single triplet from the double?
Yeah, in this, that's basically a matter of playing with this gate here, like how much you hybridize the two quantum dots. In this case, they operated it as mostly the center qubit.
Yeah, but how did they understand that? So what's the difference in the experiment? Because there's two states.
Yeah. I would say that basically a single triplet qubit is almost the same device. But the pulse sequence, I didn't want to talk about single triplet qubit today because we don't need it for tomorrow, so I only want to briefly touch upon it. But in reality, it's almost the same device, but the gate sequences that you apply is quite different, and the system needs to be tuned up a bit different. So I would say, because of the strategy they followed in this experiment, and the gates they used, and the pulses they applied, this type of scheme, you can be pretty certain that this is what they implemented. For a triplet, single triplet, ST0 qubit, this looks quite different. But the device is almost the same, I would say. Like, and people did it a few years after, right?
But the difference between the intensity with the upping into speeds. So the low intensity coupled to each other. Otherwise, they force states.
I think I agree, yes. But then to allow some tunneling, you need to turn the cell. Let me think. This is the plunger, and this is supposed to be. So this is the the one for loading the electron, so they're not showing what they did to any of the other gates, if they did anything or not. I suspect they had a weak static tunnel coupling between the two dots on that allowed for, with some tunnel time, that allowed for this tunnel process to happen. But that they, because for a singular triplet qubit, singular triplet qubit, you really find different pulses where you're playing with the detuning of the dots, so you're doing something to both dots. And then you pulse in this level scheme back and forth. And they didn't do any of that, right? Like, people worked that out a few years later. But in all fairness, I'm also wondering, of course, like, this is a fully confined control field, right? Like, why is nothing happening to this spin? Let me sleep on that. Maybe I come up with a good answer tomorrow. Yeah?
What do you mean by power?
Sorry, say again?
What do you mean by power?
This is the microwave power of the source, so that is basically at the top of the experiment how much microwave power you send down, which then translates into the amount of current here. So really, power, there is a square root difference there between power and effective magnetic resonance field. But really, this axis here, the power difference tells you the strength of the driving field. So how fast your radio oscillations are. You can see that as they go up in power, the frequency increases. Mind you, like, this is historic data. This is like the first time this was ever observed. And there is like a few oscillations visible. They barely managed to see any coherent control, and yeah, they swept this microwave power, and that determines the oscillation frequency. The more power you apply, the faster you will flip the spin. Okay? There's a square root difference between power and microwave. The B in the microwave field, the magnetic, the time varying magnetic field. And it should be linear. That like comes out of the Rabi model basically, and that tells you have a normal first order transition if you have linear dependence between the drive field, the size of it, and the frequency. That's typical measurement people do. Now this is how it looks in a modern experiment. So that comes basically back to your T2 question. In modern, this was gallium arsenide almost 20 years ago now. There's barely anything visible, but this is what we can do today. We can have beautiful Rabi oscillations in these systems. So this is a line cut through the center. This is when you move away from resonance, where you're driving. Yeah, this is typical measurement you do for qubits. And it's really, for single qubits, it is really quite good. It is, in terms of gate fidelity for single qubits, this is in the 99.9 range, I would say.
So what is the mystery? What is the trick?
I would say
it seems quite natural that T2 is short because there is a you operate with charge in order to actually operate with speed. And charging energy scale is large. So what to do to avoid?
Improve the material and the device fabrication to get exactly this under control. So change the material to something without nuclear spins. It's very important. You have no randomly varying background, no Oberhauser field. You take that out, and then all you can do is work very hard to get the electrostatics or dynamics even, like get that completely under control or to the point that the system behaves proper. And I think that this is at the moment at the single qubit level, this is possible, but then you can cheat. You can pick the few working ones that sit in a spot where the electrostatics allow you for good coherence. But when you do this large scale, you can no longer, of course, do this because you need every qubit to be similar in quality. That is exactly the challenge I think that the systems are facing now. And it's, of course, that's I would say a die-hard material and device engineering problem. Optimize the interfaces, semiconductor dielectric interface is always the obvious one to work on, but also charge defects in the material itself, etc. And yeah, I think this is the open question. Can that be controlled to the point that you can make many qubits reliably? And the answer is at this point we don't know. We are of course like working on it. You're positive, you try and you hope. But it may be that in 10 years the progress has been so limited that we just have to decide to abort. It's never black and white, you know how this goes. Yeah. So single qubit level I would say we're fine, but getting repeatability in there. Yeah, we already discussed this briefly. Again, single triplet. I just want to quickly flash it, but now you you have a double dot system, so it's almost the same device, but you operate it differently now. Your Rabi oscillations are on this axis. Okay? So I think the answer to your question is that in the loss-leaving sensor qubit, you have this microwave line that applies an oscillating magnetic field. Okay? Because you are controlling the Zeeman interaction term that way. In the singlet triplet qubit, you are operating on the exchange in the energy. The exchange interaction is the one that causes you the rotations. And so you do it via gate pulses, the control. But I don't want to go fully through all the details now. It's not necessary for tomorrow. Can you give a better description, Sebastian? I think like you're not controlling the qubit with magnetic microwave pulses in a single triplet qubit. It is done through gate pulses.
Nobody controls
I will show you tomorrow that for the donors in silicon, we still do it with magnetic fields mostly.
what about
Sorry?
what about
No, but that is a whole different story. I didn't want to touch upon that too much, but there we have, of course, there we have EDSR. So we have, because spin orbit, spin and position are now coupled, so we can use electric potentials there. That's a different Hamiltonian term. So on the Zeeman interaction, we're modifying either the G factor or the spin orbit interaction with gate voltages. Using that this type of single triplet qubit was the same, exact same material system, same device, but now by playing with gate voltages, you can control the qubit by putting pulses on the gate. What I really wanted to say is that you have different encodings. We have loss-leaving sensor, we have single triplet. What you are doing now is, rather than having a pure spin degree of freedom, you're adding a second electron in there and you're making a hybrid of spin and charge. That is now, the qubit is no longer a pure spin qubit alone, there's also a charge component to it. Yeah, so operations are in the gate space, you don't need magnetic controls. The readout is pretty similar. You can also add a third quantum dot to the system, and you work on a coupled 3-electron system and its spins. There you don't need the background magnetic field anymore. Remember that for the single triplets to split them, we still need a background magnetic field to create some energy splitting. The whole point I want to convey is like we have these different encoding schemes. It seems that the optimum is maybe single triplet or loss-leaving sensor qubits, the pure ones, but this seems to be a lot of overhead to encode a single qubit to have 3 quantum dots in terms of gates, etc. But it can be done. I'm running out of time. This is how you do a dephasing measurement. Basically what you do, you have your, in this case, single triplet or spin up, spin down. If it's a loss-leaving sensor qubit, you rotate it to the equator with a pi 1/2. You let it evolve, and you rotate it here, and you look at what you get, basically. That is called a Ramsey measurement. And yeah, you can do that. You can see the decay of the qubit, and that gives you what we call T2 star. So this is the dephasing time of a qubit comes out of this measurement. And then you do this average over many shots. It's a statistical property. Of course, we can play some tricks that we let the system evolve for a while, it jitters, it gets randomized, and then we apply a pi pulse. And all slow moving, all slow noise will be subtracted from the phase evolution of the qubit. Okay? So this is a simple, it's called spin echo, it's a simple rotation around the z-axis by pi. And then you can apply many of these sequences, you can play more complicated tricks, and then you end up into a dynamical decoupling of a qubit. Okay. But this is sort of the pulse sequence. You have these wait times, and then when you do the pi change, another wait time that should be equal length to counteract all slow variations. You do that, you get this is called a Hahn echo. So you get in papers you will see written T2 Hahn. And that is typically a longer time scale than T2 star, and then you can apply more complex games to keep the qubit coherent longer. CPMG is a very popular one, popular pulse sequence. Anyway, this is another example of for a single triplet qubit. You can see that nowadays you can have beautiful Rabi oscillations, and the T2 stars are decent, 18 microseconds. I think the operation speed is high enough that you can do whatever, 1,000 operations or so, or 10,000 at the single qubit level. This, what do we want to do? Do we want to carry this over to tomorrow or go 5 minutes over time? Who's the next speaker? Huh?
I think there's no break.
Okay. So then I'll just finish it off, okay? This is. I already mentioned this multiple times, but gallium arsenide has nuclear spins in it. And you cannot find stable isotopes without nuclear spins. So that means that you have whatever, 10% of your spins or so, I forgot what the numbers were in gallium arsenide, but a large amount of nuclear spins. And this is a whole field of study in its own right. It forms like a nuclear spin path that has complex dynamics. It's called the Oberhauser field, a background magnetic field, but it is slowly varying with multiple frequency components, etc. in there. It's complex. Turns out that you can counteract it somewhat doing these decoupling pulses that I just showed you briefly, but in the end, it's just not good enough to keep going forward. So that is where silicon and germanium come in and are very attractive because they can be purified. So silicon has silicon-29 as the spin 1/2 isotope. This can be purified. You basically need cyclotrons and things that are used in the nuclear industry, often the shady nuclear industry, key towards defense, so it's always complicated. But yeah, by now the demand in our community has been high enough that if you pay enough money, you can get a bottle of precursor gas that has silicon-28 in it without silicon-29. And you hook that up to the growth reactor and you can grow top layers of your substrate where you make the qubits isotopically purified. And that means, and this is like, I will show an example of that tomorrow for donors in silicon, this is like a difference of day and night in the performance of these spin qubits. Okay? The other big reason why silicon-based platforms using silicon substrates, etc., are very attractive, of course, it's a dream we all have in this community, is we can dream of the established semiconductor industry's capability and very advanced fabrication techniques. Of course, this is at this point a dream, like adaptation is only just starting to happen now, I would say, in the last few years. Very difficult, of course, to make these very academic quantum devices into something compatible with an industrial foundry. It's a challenge in its own right, but people are starting to actively work on that. So what are the options for quantum dots? We always need quantum dots, right? Like well-defined quantum dots. We have dopant atoms in gold silicon is a real option. This one, I would say all these lower dimensional structures are not so attractive from a scaling perspective. The other ones are to have silicon oxide metal, so silicon MOS, and work at the silicon oxide interface right here, or work with silicon germanium heterostructures. Okay? So the thing to remember with silicon that its band structure is not so easy to work with from a spin qubit perspective. The reason being is that here you have a 6-fold degenerate band gap bend in the bulk. Okay? That's a problem because for qubit definition we cannot have a degenerate band structure. We need to have all the degeneracies lifted. So that is why strain or confinement at a silicon interface that helps you a lot. You get rid of at least 4 of the bands, you split them off, but the 2 are always near degenerate. And that is one of the main bottlenecks in silicon, I would say. So the lowest, this is called the valley splitting, and this lowest nearly two-fold degenerate state is problematic from a scaling perspective. It's of the order of half a millivolt or 1 millivolt, which in energy scales is just small enough to be annoying. Like big enough that you can do something, but small enough that you need to worry about it. So that is a problem with silicon, I would say. In dopants, it's a bit easier to work with. I would say, yeah, that splitting is a bit more. We don't need to worry much about it. The dopants are more difficult to scale and couple. So it's one thing, and that is, I think, why silicon was so much harder to work with, and still till today remains difficult, is that the effective mass of silicon is relatively large. This is a factor 4 or 5 larger than in gallium arsenide. And from a lithographic perspective, think about it of a particle in a box. Low effective mass means that the wave function is more smeared out in the material, and your box that you make for it can be larger. Meaning that lithographically, it is much easier to confine a single electron in gallium arsenide with its smaller effective mass than in silicon with its larger effective mass. On top of that, the material is much more disordered than gallium arsenide, so that was also problematic. And really, I think the fact that we only in the 2010s, I would say, got reliably spin qubits in silicon reflects that. Yep.
So you mentioned the degeneracy, the remaining two-fold degeneracy, but isn't it lifted exactly by confinement? Because you can make this gap as large as you like.
The remaining, the 4 bands that you split off in the heterostructure, for example, due to strain, you can forget about.
Yes.
The remaining degeneracy is basically due to confinement, the confinement potential, etc., in the quantum well that breaks that degeneracy as well, but it is small. You have very little control over it. It's very experimentally, like it's determined by the growth parameters, the parameters of your heterostructure, and then you can, I think, tune it a little bit with electrostatic gates, etc., but not enough that you can.
Well, maybe I'm incorrect with this. But when I usually measure a two-dimensional electron gas, I already have my motion quantized in perpendicular direction, and this gap is already relatively high, right? Or not enough. And then you confine it in the direction which is in plane, and you get rid of it entirely. Or am I wrong at this point?
Well, the confinement you get into the is for the orbital states of these electrons, right? It doesn't remove the band structure degeneracy itself, I would say.
Yeah, but then we're talking about the wave function of a single electron, and if I have 2 such wave functions corresponding to different mass, they will correspond to relatively different energies, right? Maybe I'm missing something obvious here, but...
Let me repeat the right answer.
So, I don't think that is the problem. I don't think they are that different. They are really near degenerate, the 2 remaining ones.
Okay, maybe postpone that.
I'll also suggest that we end it here and postpone this next time. Because
Yeah, this you can skip, it's not so important. It's just saying that it works, it can be done. The only thing that is nice is to look at this, then we are just done. So this is the state of the art in spin qubits at this point in time, I would say. So you have, you have a chain of 6 spin qubits. All the individual spin qubits are really good. they have high fidelity, but the problem is in the 2-qubit gates, the fidelities are too low. Also, I would say making this reproducibly, that you have 6 of these qubits all working so well in a single device is very difficult. But the problem is here that, with these type of fidelities, some of them are getting quite high, but some of them are way too low, and that means that if your conditional gates between the neighboring qubits are of this quality, you cannot easily create full entanglement across the chain. Like you cannot. You can entangle neighboring qubits, yes, but next to those neighbors in this device already gets very difficult. And in all fairness, that is, I think, a material engineering and device engineering problem that everybody in the community works hard on to try and fix that. That was pretty much it. Other active areas of research are, of course, alternative platforms, germanium, silicon germanium, building on-chip links. Spin qubits are very dense, so at some point you need to be able to branch out all your lines, and then you need to have an on-chip link to go to the next cluster of spin qubits. So I think from an architecture viewpoint, there are many open questions there. This we will see if germanium performs better than silicon. I think it's an open question. There's many attractive aspects, but also some drawbacks. So we will see. It's part of our team's effort to contribute to answering that. That was it. Sorry that I went a little bit over time. Tomorrow we continue with nuclear spins. Now I only talked about them as a nuisance, something we had to get rid of. We reintroduce them tomorrow. Okay?
Maybe I realized my confusion. So the remaining two bands, will they have equivalent identical